Yeah, so that's on. Yeah, I'll take a look at the graph. I mean, it's not in the shapes. It's just like we're moving toward the first graph. We're not in there.
Do you know if your Zoom is using this microphone or your laptop?
Oh.
Usually it automatically switches. That's
Find
good.
out.
Probably. Oh, yeah. It's in the top.
Yeah. I wonder if, oh, can I drag this back here? Will
Yeah,
that?
that would be good.
Let's see.
Just click the little button.
Yeah, thank you. Jabra,
Yep.
that sounds like your
Yep.
thing. Okay. I just need this. Okay.
Okay, I think we're 50.
All right.
If people 3 seconds for a minute. Okay.
Sure.
All right.
Radial. All right, it is my pleasure to introduce Lauren Weiss, a professor of physics at the University of Notre Dame. Lauren started her astronomy career at Harvard as an undergraduate. She got her PhD from the University of California, Berkeley, working with Jeff Marsky on aspects of the Kepler mission. Lauren was a postdoc at the University of Montreal, at the University of Hawaii, before moving to Notre Dame I think just in the last year, if I have my dates right. Lauren is especially known for studies of small planets from the Kepler mission. Lauren was, I think, the first to show that the smallest planets discovered by Kepler have high bulk densities and became compositions similar to the Earth. And Lauren also was the first to show this idea of peas in a pod, which I think we'll hear a little bit more about today, of the self-similarity of planets in the same planetary system. So welcome, Lauren. Let me also remind folks that we are back on with wine and cheese. I will follow this immediately, and it's going to be out on the patio tonight. Thanks, Lauren.
All right, thank you so much all for having me here. It's a pleasure to be back in Caltech, and I'd like to apologize to those of you with whom I missed meetings today. I'm sorry, my long-term health is not the greatest right now, and I aspire to give a full good colloquium today, but don't feel like making any promises at the moment. For those of you who don't know me, let me introduce myself. This was working. Turn it off and on again. Maybe. All right, well, I can do, actually, wow, that isn't working at all. How bizarre, hang on. Let's see, if I pause sharing, does that fix it? No. Okay, apologies for the technical difficulties. All the difficulties are mine today, apparently. Let's just try again. Ah, there we go. All right, so let me introduce myself for those of you who don't know me. I was born in the year 1987 on a small, mostly rocky planet, third out from the sun in what at the time was the only known planetary system. And of course, today we know of over 5,000 exoplanets in over 3,000 unique systems, or sorry, 2,000 unique systems, hosting a multitude of planets. The majority of these are transiting planets, smaller than Neptune, and closer to their stars than Mercury is to our sun. So there are a few key questions we have about these planets. What are the compositions of these small planets? How did they form? And could they support life? I'd like to introduce the idea that planet mass is a critical quantity to answer these questions. Planet masses are just key for understanding the interior compositions of planets, their atmospheres, their dynamical histories, and for interpreting any putative biosignatures that we might find. Unfortunately, planet masses are also the bottleneck in our understanding. Of these thousands of planets, there are only a couple hundred, about 10% of these sub-Neptune sized planets have measured masses. So let's just quickly review how these planets are discovered and characterized. I think most of you are familiar with the ongoing NASA TESS mission, but before TESS, there was a beautiful mission called Kepler. The prime mission was 4 years, and this was designed to study the statistics of exoplanets. And it was capable of finding Earth-sized planets around sun-like stars. And it did this by detecting the transits of planets across their stars. Kepler's secret to success was that it continuously stared at 150,000 stars for 4 years in a region of the sky just above the band of the Milky Way. And with this long baseline, it was able to find small planets far from their host stars if they happened to transit. The Kepler mission discovered over 4,000 planet candidates, the majority of which are probably real. The majority of these planets are close to their stars with periods less than 100 days and sizes between that of Earth and Neptune, which notably is not represented in our solar system. So how do we learn about the compositions of these small planets? Well, what I've been doing in collaboration with Andrew Howard for a long time, the past decade, is using this big, beautiful mountain we have called Mauna Kea, which has some telescopes atop it, including the W.M. Keck Observatory. And this is the facility with which we measure the masses of small planets. The method we use is based on fundamental principles of physics. Although we're searching for a planet, we know from Newton's laws of motion that the star must also be orbiting the center of mass of the system in an orbit identical to that of the planet, but smaller in size and opposite in phase. We measure the forward and back motion of the star via its Doppler shift through a high-resolution Echelle spectrum. At the moment, the tool that we use is the high-res instrument, and those of you who know Andrew know that KPF will soon be online. To investigate the compositions of planets, we want to measure their bulk densities. So the strategy here is we go to the telescope night after night and measure many Doppler shifts, which are required to get the mass of the planet. We then divide the mass by the volume, which we know from the cross-sectional area that the planet blocks during transit, to get the planet's density. So for context, let's look at the densities and radii of the solar system's small planets. The terrestrial planets and Earth's moon, which are gratuitously located on the left side of this plot, are mostly consistent with Earth-like compositions, although iron-rich Mercury is an outlier. Uranus and Neptune, which are on the right side, have substantial volatile envelopes. So some of you might know already, but for those who don't, where do you think the exoplanets with measured masses and radii will fall on this plot? Here they are. So here are the 200-something exoplanets with measured densities. So what can we learn from what we've measured in these planets so far? Back in 2014, I led a breakthrough discovery about the compositions of small planets. We realized from this data that rocky planets, by which I mean planets composed of a mixture of silicates and iron, are typically smaller than about 1.5 Earth radii. This distinction is illustrated by the change in slope of the thick gray line going through the gray data points. So rocky planets, which are on the left side of this plot, have a density that increases with size due to the compression of rock. However, planets that are larger than 1.5 Earth radii decrease in density, and this must be due to an increasing admixture of volatiles in their bulk composition. Our result was it's one of the most cited results from the Kepler mission. And what's kind of cool is we did this back in 2014, and now years later, the exoplanets still seem to follow this pattern. So these mass radius relationships are still a good predictor after 8 years of new data. So you might wonder, why rocky planets? Why do we care about them? And the reason is that rocky planets will help us look for biosignatures. My colleagues in biochemistry tell me that life does really well on a substrate. Chemical reactions proceed faster in 2 dimensions, which can happen on a rocky substrate than in some like 3D suspension in gas. So rocky planets, or rocky surfaces in general, are good places to support fast chemical reactions conducive to life. So we'd really like to find more rocky planets, understand how they form, and then eventually look for biosignatures. And KPF has an incredible opportunity to be the leader in this parameter space. There are a variety of extreme precision RV spectrographs coming online, and they're all going to contribute to this effort. And I in particular will be using KPF hopefully forever and ever. So one way to summarize what I just told you about small planets is that different kinds of planets have different ratios of gas and solids. The terrestrial planets and rocky exoplanets are almost entirely made of rock. But as we just saw, slightly larger planets, which are still mostly rock by mass, can have a thin veneer of a volatile envelope that substantially changes their density. Even more extreme are the gas giant planets, which are mostly gas by mass. So the materials in these exoplanets are, of course, related to how they are now, but also are related to the conditions in which these planets formed. So we'd like to understand how planets form and change over time. And one way we can do this is by studying systems of different ages. So my team recently discovered a rocky world that has existed since the dawn of the Milky Way galaxy. Its age and interior composition provide a critical data point about how the earliest rocky worlds assembled. This discovery was part of the NASA NASA Keck strategic mission called the TESS-Keck survey. It's a multi-institutional team on which I'm a co-I, and our survey supports and enhances the TESS mission with radial velocity follow-up. So for this particular system that I studied, the biggest surprise was that the planetary system orbits a star in the galactic thick disk, a population of old chemically distinct stars in the Milky Way. So as part of our survey, we obtained a high-resolution spectrum of this star. And the spectrum shows that the star has a low iron abundance and is enhanced in alpha elements. This chemistry, combined with the star's kinematics that we know from Gaia, are consistent with thick disk membership for the star and an isochrone determined age of 10 plus or minus 3 gigayears. So this is perhaps the oldest rocky planet yet discovered, and it's the first rocky world around a galactic thick disk star that has been confirmed with radial velocities. We can gain insight into the composition of this planet by placing it on a mass radius diagram. The planet in question is indicated by the big blue arrow, but it also has a couple of neighbors, which you can see. What you might notice here is that planet B has a slightly lower density than what is average for planets of its size, suggesting that the interior might be iron poor. So perhaps this planet inherited an iron poor composition from the same nebular material that formed its iron poor host star. Of course, you might notice that's a pretty big error bar on the planet density, and a better mass measurement would certainly help determine the composition of this planet. My PhD student, Casey Brinkman, has significantly improved the mass measurement of this planet using Gemini's new precision RV spectrograph, Maroon X. She obtained the most precise RVs yet of TOI 561, which are shown in the yellow. You can see how much lower the scatter of the yellow points is than the blue. And by combining all of the existing RV data, she got a mass of just a little over 2 Earth masses with just 10% uncertainty in the mass. This does indeed correspond to a low density planet consistent with either an iron poor composition and also quite possibly a volatile envelope, which would make it the only sub 1.5 Earth radius planet with a volatile envelope yet discovered. Casey's thesis will continue to address the relationship between planet compositions and the elemental makeup of their stars. So speaking of stars, characterizing exoplanets requires an accurate knowledge of a variety of stellar properties, including their metallicities and radii. At the time, the majority of the Kepler planets were detected, their host stars were very poorly characterized with typical errors of about 40%. And the stellar metallicities were unknown. As you might know from Andrew and BJ's work, we conducted the California Kepler survey to gain accurate information about these host stars and apply this information to our understanding of the planets. We collected high resolution spectra on Keck HiRes of 1,300 sun-like stars hosting over 2,000 exoplanets, creating one of the largest homogeneous catalogs characterizing the host stars of Kepler planets and then the planets themselves. Without accurate host star properties, the distribution of planet radii looked like this. And you probably know what's coming next. With our newly conducted survey of stellar radii, we were able to improve the precision of planet radius measurement and found that the planets cluster in 2 sizes with very few planets near 1.8 Earth radii. So this is of course called the Fulton gap. And part of how we were able to interpret what's happening here is that the Fulton gap perfectly lines up with that peak of the density radius distribution I just showed you. This alignment allowed us to conclude that the 2 clusters are linked to 2 different compositions of planets, with rocky planets on the left side of the gap and planets that have a thin volatile envelope on the right side. We already understood that planets on one side of the gap were rocky and on the other side they were volatile rich, but the discovery of the gap itself was new. So how does nature produce a gap in the size distribution of small planets? This is still an open question, but the key is in understanding what happens to a planet's composition when that planet is heated. Assuming that the planets all assemble as rocky bodies that then accrete some gas from the nebular material, we can think of planets as a simple 2-layer model with rock and iron on the inside and a layer of gas on the outside. Heat can remove gas from planets. Massive planets and planets that are far from their stars can hold on to their gas much better than the low mass planets. And this is what creates the gap. So this is a lovely aspect of planet formation and hints that we really don't understand the physics that's going on when planets form. One of the best ways to test the physics of planet formation is to study multiplanet systems. In these systems, the planets all formed around the same star and from the same protoplanetary disk. And so they provide a controlled laboratory from which we can study planet formation and evolution. So let's review the architecture of the best studied multi-planet system, which is, thank you, our solar system. So our planets lie in the ecliptic plane and have nearly circular orbits. We have terrestrial planets close to the star and gas giants beyond what's called the snow line. And we're just beginning to probe the structures of distant Kuiper belt objects. The solar system has been observed by astronomers for a long, long time, and they have looked for patterns in the architecture of the solar system planets. Johannes Kepler was fascinated by patterns in nature. He once said, "I do not believe that even in a snowflake, this ordered pattern exists at random." And famously with the solar system, well, of course there was Kepler's laws, but a bit lesser known is he tried to explain the orbital periods of the planets as a series of nested platonic solids, which worked to a point, I think, and then didn't. A few years or a few centuries later, Titius noticed that there is a regular geometric progression in the planet spacing, a relation that is sometimes called the Titius-Bode law. Of course, with the burgeoning number of not only planets, but planetary systems, we can begin to look for patterns beyond the solar system. There are over 700 detected multi-planet systems with nearly 2,000 planets, 1,400 of which are transiting. Most of these are from the Kepler Prime mission. TESS doesn't have a long enough baseline to find very many multi-planet systems. But still, this is a wonderful statistical sample in which to look for patterns. As part of the California Kepler survey, my teammates and I measured the properties of 909 transiting planets in 355 multi-planet systems. The planet orbital periods and transit depths come from Kepler, and our additional contribution was to measure the stellar properties and gather precise planet radii with high resolution spectra from Keck. This is part of our big uniform CKS catalog. So I guess what I'm showing here is a subset of the multi-planet systems. I can't show you all 909 at once very easily, but these are the 51 CKS systems that have 4 or more transiting planets. So let's take a look. And what I'd like to tell you here is each dot corresponds to a planet, and each row is one planetary system. The planet's semi-major axes are logarithmically spaced on the x-axis, and the sizes of the planets are to scale. So with that information, do you see any patterns here? Especially for people who don't already know the answer. All right, so the pattern is that planets in the same system often have similar sizes and regular orbital spacing. So now a new follow-up question, anyone can participate except for Constantine. Which systems on this plot best exemplify this pattern? I suppose it's a bit small for you to see. I'll give you a hint. It's either the top or the bottom. Top, yeah. So these systems are ranked by their size dispersion, where systems with more uniform sizes are at the top and less uniform sizes are at the bottom. By the way, this figure is from a review chapter that I've authored. Constantine is one of my co-authors, which is why he wasn't allowed to answer. But it's been an absolute pleasure working with these folks on a review article, which will form much of the rest of my talk. At any rate, we call this the peas in the pod pattern. And there are a couple of different ways that we can quantify this pattern. One is to look at the size similarity. So what we did here is we took pairs of adjacent planets in the same system and compared the size of the inner planet, which is shown on the x-axis, to the outer planet, shown on the y-axis. The sizes of the adjacent planets in the same system are significantly correlated, with the correlation spanning from Mars-sized planets down here. Sorry, I guess folks on Zoom can't see that, to Jupiter-sized planets in the upper right. This sample includes planets in systems with multiplicity 2 or larger and spans 504 unique pairs of planets. You might wonder if this pattern is somehow linked to Kepler's detection bias. It's easier to find big planets than small planets, but that bias is well known and we can mimic it. By drawing planet sizes at random in a way where the planets don't know the sizes of their neighbors, and then simulating Kepler's detection bias, we produce the plot on the right, which, as you can see, doesn't actually look like the observed pattern. Another pattern that I mentioned was regular spacing. So how do we do that? This is basically the same story. We took the systems with, in this case, 3 or more transiting planets and compared the ratio of their orbital periods for the innermost planet, which is shown on the x-axis, to the next pair on the y-axis, etc., iterating through all the available triples. And you can see there's significant correlation here as well, with so a lot of white space in the upper left and lower right corners of this plot. Again, we can draw planets at random to simulate Kepler's detection bias, and we get something totally different. It's important to note that although the period ratios in these compact multi-planet systems are regular, they are not resonant. The black line shows the distribution of period ratios in the compact multis, which is well described with a log normal distribution. But note that there are very few planets that are in or very close to these mean motion resonances, which are highlighted with blue and gold. These peaks have nothing to do with P's in a pod. Rather, the period ratios of a few exemplary systems are shown as solid lines beneath the histogram. And what you can see is that the period ratios in a given system are clustered, but not usually near a resonance. Another pattern that we might notice is that there seems to be some relationship between size and spacing. And this is, of course, interesting if you care about how planets grow. So if you look carefully, you can see the tiniest planets on this figure are quite close together, and the bigger ones are a bit further apart. So what we did here is for each system of 4 or more planets, we are plotting their the typical period ratio in the system on the x-axis and a typical estimated mass on the y-axis. I used the Weiss-Marcy mass-radius relationship because we still think it works. And what you can see is there's significant structure to this plot, with the smallest, the lowest mass planets having very close period ratios, and planets that are a bit more massive having a further wider period ratios and also a greater diversity. Furthermore, we've colored the points by their mutual Hill radii. And what I hope you can see here is that the Hill radius is not actually a good predictor of this pattern. That it's not something about the Hill radius that determines that the close planets should be small and the far apart planets should be big. Let's see, a common misconception that I'd like to address is that the stellar mass or metallicity is somehow responsible for the P's in a pod structure. This is not the case. Within just a few tenths of a deck in stellar mass, we can see that the typical planet size of the most P's in a pod-like systems, which are highlighted in black, varies by a factor of few, whereas the size dispersion, which is indicated by the tiny little vertical error bars, the size dispersion is much smaller than order unity. So while the stellar mass and metallicity might have something to do with like an upper envelope to this whole distribution, the largest possible planets that might form around a given star, they do not appear to be the dominant factor in setting the size of the P's in a pod pattern. A remark I'd like to make is that, of course, TRAPPIST-1 was not in our sample. It's not a part of the Kepler survey. But if we were to add TRAPPIST-1 to this plot, that is a star that is 0.1 solar masses and has a whole bunch of Earth radius planets. So it would live way out here on the left and at a height of here. So if you add that point to the plot, it certainly shows that that any correlation here is quite weak. All right. So now that we've looked at a whole bunch of patterns, let's see how the inner solar system fits into this picture. Earth and Venus have nearly identical size, mass, and interior compositions, but their neighbors, Mercury and Mars, are much smaller, with Mercury having less than half the radius of Earth and approximately 1/20th of Earth's mass. So what did the terrestrial planets look like compared to the peas in a pod structure? Well, here they are, again, still ranked by their size dispersion. And you can see that most compact multis, in fact, 80% of them, have more uniform sizes than the inner solar system. Another way to think about this is that, when we learn about the terrestrial planets in a textbook, we think, they're all rocks, they're all the same. But actually, they are much more diverse in size than the majority of 4-planet exoplanet systems discovered so far. We computed 2 metrics to describe these compact multis, a log radius dispersion, which I've been showing you so far. That's now plotted on the x-axis of this plot, but we also might care about the spacing regularity. So we have a log spacing dispersion plotted on the y-axis. In general, the peas in a pod, the compact multis generally have both size regularity and spacing regularity and are clustered toward the origin. And most of these planets have more uniform sizes and regular spacing than the solar system. Thus, the so-called Titius-Bode relationship within the solar system, in a sense, is typical, or perhaps even anomalously irregular compared to the exoplanets that we've been discovering so far. So, in a sense, the Titius-Bode relationship that we live within is a poor example of what's actually a much deeper and greater pattern within nature. In addition, we can use this metric to identify outliers that have small size dispersion, but large spacing dispersion. These are systems that have a clear gap in their architectures. There is likely a planet in the gap that either transits but was not detected or does not transit at all. And looking for these planets should be a lot of fun. So this highly structured peas in a pod pattern is a common outcome of planet formation that was not anticipated. The low entropy nature of the pattern appears to be at odds with classic textbook examples of planet formation, which do not explicitly predict such regular order in planetary systems. So this is an opportunity for us to revisit planet formation and look for processes that might give rise to such a pattern. A couple of years ago, Adams, Batigan et al. Considered energy optimization as a framework to describe the emergence of this pattern. Their key insight was that the planet's self-gravity is important, and so they included it in their Hamiltonian. By optimizing the energy of the system, they found 2 different solutions for how the mass can be distributed among the planets. Below a critical mass, the energy of the system is optimized when the planets are all basically equal mass and regularly spaced like peas in a pod, as illustrated by the blue points. However, above a critical mass, the energy of the system is instead optimized when one of the planets undergoes runaway growth and dominates the mass budget of the system, like the red dot. This critical mass is dependent on a variety of factors, including orbital separation. And so this energy optimization idea makes a prediction that far from the stars, the peas in a pod pattern should break down. This is something that I would love to test with KPF. Another interesting thing about this theory is it is actually agnostic about the mechanism of how the planets become similar in size and regularly spaced. It's simply pointing out that this is the energy optimum. So what is the mechanism by which planets become peas in a pod? Something that I learned while we were writing our chapter is that the peas in a pod architecture requires an inward migration of solids. The reason for this is that the surface density of the fully assembled peas in a pod systems does not match the surface density expected from star formation. In general, we think about a disk profile as having a power law index P. And note that for equal mass planets at regular spacing, the power law P has to be 2, whereas star formation theory predicts a less steep profile, typically P of about 1.5, and ALMA measurements of outer parts of solar systems have P of more like 1. So there's some tension here, and it seems like a radial redistribution of solids is needed to steepen the power law index close to the star in order to form the peas in a pod pattern. But what's great is we've got a lot of mechanisms to get planets closer to their stars. In particular, orbital migration is very helpful. And this can happen through a variety of different mechanisms. Pairwise collisions is one promising avenue, which eventually results in giant impacts. And pebble accretion is an interesting alternative. But at the end of the day, you've got to get the material transported inward to make peas in a pod. So we had a population synthesis component to our chapter, and I was delighted to see that we reproduced several aspects of the peas in a pod architecture with the Bern model of population synthesis. Again, the observed compact multis are on the left, and the synthetic planets, which seem to resemble somewhat the peas in a pod, are on the right. There's been some success with this approach before. Mishra et al. Successfully reproduced the observed size correlation, and again showing the observations on the left and the results from population synthesis on the right. The major advantage of PopSynth is that we can study how these patterns emerge and change over time. Our simulation seeds the planetesimals with very, very close orbital spacing, and as time progresses, the protoplanets undergo more collisions, which results in a more relaxed distribution of period ratios. This is especially notable at the time of disk dispersal. Compare the green histogram to the blue histogram. Additionally, although some planets appear to get trapped in or just outside these mean motion resonances, the majority of planets are not and seem to fairly well match the Kepler distribution. The peas in a pod pattern is only part of the literature on multi-planet systems. There are lots of patterns that need to be reproduced by simulations and lots of new physics to learn. So just to recap, the planets orbiting a given star tend to be similar in size and with regular spacing. There's a relationship between the characteristic size and spacing. I didn't talk about this, but the outer planet of a pair tends to be larger if there is size difference. And planets are rarely in mean motion resonances, although they might have been there at some time in the past. All right, so right now I'm investigating whether the composition diversity of the terrestrial planets is unusual. We've already discussed that Venus, Earth, and Mars have Earth-like compositions, whereas Mercury is an iron-rich outlier. So we might wonder, do exoplanet systems have more or less diversity in their small planet compositions than the solar system? To answer this question, I've been conducting a radial velocity survey of the composition diversity in multi-planet systems using Keck HiRes. This is a NASA Key Strategic Mission Support Program, fulfilling the Kepler mission's legacy to understand planet architectures and compositions. So I'll show you a few highlights from this survey. It was a magnitude limited survey because most of the Kepler stars are quite faint. So this is a system where the planets are like peas in a pod, similar in size and regularly spaced. And our preliminary analysis also finds that they have similar compositions. You can see they're all on the volatile branch of the density radius diagram. Here's another system where the planets are similarly sized, but these are 1.5 Earth radii and appear to have high densities consistent with rocky compositions. However, not all of the systems look like peas in a pod. This is a system that has some size diversity, and I'm going to work with an undergrad this summer to test whether this could be a site of photoevaporation or not. We also have some systems that have apparently diverse densities of small planets, including, albeit with larger error bars, potentially high densities suggestive of the mantle stripping that Mercury underwent. So here are the four systems together, some with similar compositions and some that have composition diversity. These are preliminary results. Please don't tweet, by the way, but hopefully they'll come to you in a paper soon. The other ongoing research I'm doing is studying whether giant planets help or hinder the growth of Earth-like planets. So far, we've mostly discussed small exoplanets and whether or not they're like Earth. But as we know, Jupiter and Saturn played an important role in the formation of terrestrial planets. They might have helped keep our terrestrial planets small and possibly directed water-bearing comets toward the Earth, influencing or perhaps even causing the origin of life. So giant planets are important. From Doppler surveys, including CLS conducted by Lee Rosenthal, we know that roughly 20% of sun-like stars host giant planets. What is not yet well understood is whether giant planets help or hinder the growth of Earth-like planets. I'm leading a long-term survey to investigate how the properties of giant planets relate to small transiting planets. Our survey has been ongoing for 10 years and has targeted 57 Kepler systems with transiting sub-Neptune-sized planets. Our objective is to relate the masses, eccentricities, and orbits of the giant planets to the number, sizes, and orbits of the small planets. So far, we've discovered 11 new planets in 10 systems and trends from stellar or substellar companions in 3 systems. And this survey is going to help us determine whether giant planets are helping or hindering the growth of terrestrial worlds. A quick comment is that I was looking the other day, and it's the first survey that spans 4 orders of magnitude in semi-major axis and 7 orders of magnitude in companion mass for planets within the same system. So star, planet, brown dwarf, they are all just balls of dynamical formation. My student Jingwen is participating in this survey. For her first-year project, she discovered and characterized the orbit of a massive giant planet in a system that has 2 transiting sub-Neptunes. We were lucky enough that the host star has astroseismology, and she was able to characterize its obliquity from this and found that the sub-Neptunes are misaligned with respect to the star that they're orbiting. She also determined the inclination of the giant planet based on analytic theory and n-body simulations. So this is one of the first multi-planet systems for which the orbital inclinations of the planets have been measured. And in particular, it's misaligned. So this will provide a valuable benchmark for understanding planet formation. All right, I mentioned that the survey spans 7 orders of magnitude in M sin I and 4 orders of magnitude in semi-major axis. Please don't take any photos or tweet. But an interesting pattern that's emerging, still very tentative, is that it appears that stars might stunt planet growth, whereas giant planets do not. What's happening in this plot is that each system has a little number labeled over the planets in that particular system. And the points are colored by the color of the most massive body in the system. So planets that are yellow have a stellar mass companion, and planets that are darker colors have more like Jovian mass companions. The yellow points down here are the smallest mass planets. These masses are from extending the Weiss-Marcy mass radius relationship, which we can probably do for Mars-sized planets because they're rocky, and if they're not rocky, they're even lighter. So these are realistic masses. And then these guys down here that are yellow have companions up here that are stellar mass companions at large semi-major axes, and it turns out actually several of them have high eccentricities. So I think that these stars might be somehow truncating the disks of these planets and preventing the radial inward migration of solids that would normally feed these planets and help them grow into big adult planets, and they get stuck as baby planets. Whereas up here, you can see a darker distribution of planets, sub-Neptunes, that have more Jovian-like companions. And these guys grew up to a nice, healthy 10 Earth mass, more typical of your Kepler sub-Neptune. So anyway, that's what I think about these days. Let's see, wait. All right, so I'd like to finish with some remarks about the future. So as we know, the Keck Planet Finder is on its way, with many thanks to the people in this audience who are making this incredible instrument possible. This is an image of the sun, courtesy of Ryan and Andrew, and you can see the beautiful orderlets, I think they're called, of the sun. And I think, is one of these a calibration fiber or sky fiber or something?
There are two fibers, both illuminated with sunlight.
Okay,
And one of the fibers is split into 3 orderlets, which is why there's 4 total.
I see. So this is the sun. You can see some of these dark bands here are the telluric lines of Earth's atmosphere, the first detection of an Earth-like atmosphere. But this is really an incredible tool. KPF will extend the sensitivity and magnitude limits compared to high res. This is a plot of the Doppler sunny amplitude that we expect from various planets versus the host star magnitude. And you can see high res kind of peters out at about 14th magnitude and 2 meters per second. And KPF gets to much better precision for fainter stars. And this is important for me. So for context, the Bright Multis program that I showed you lives in that high res space. It has to, because we're doing it on high res. But a highlight of my upcoming plans is to study the peas in a pod systems, and I guess in particular, the most orderly systems, but also the most disorderly systems. So I'll show you what those look like. Again, the orderly systems are up top and the disorderly ones are at the bottom. And my goal is to measure the planet masses in these systems to test, are the orderly ones really similar in mass? And for the diverse ones, the mass measurements will help us understand what their dynamical histories are. We will also be able to search for giant planet companions to gain insight about the planet mass distributions, compositions, and dynamical origins. In addition to KPF, an exciting new prospect is the ESA PLATO mission. This is an opportunity to extend our knowledge of planetary system architectures, but I think a few different design strategies are still under development. The nominal mission right now is for two-year stairs, one in the northern hemisphere, one in the southern. For comparison, Kepler was a 4-year stair at one patch of the sky. And I'm not quite sure what, with these cameras, it's got these 26 12-centimeter aperture cameras. And if it points 4 of them at each particular location on the sky, it still won't meet the photometric precision of Kepler. So this will be a wider field of view, but less photometrically precise version of the Kepler mission, which might do a bit better than TESS in terms of its yield of multi-planet systems. I'm hopeful, and certainly hopeful, for a Plato extended mission, which would just be one long stair somewhere. The reason for that, of course, is that planets that are far from their stars are the planets like ours. The study of exoplanets is a journey echoing Carl Sagan's observation that we're the part of the universe that has become conscious of itself. We are investigating our own origins, both by retracing our lineage through the cosmic events of planet formation, and also by seeking new worlds and perhaps life that can serve as mirrors of ourselves. Thank you.
Very much questions, Lee.
Awesome talk, Mark. Thanks so much. That was really great.
Something I've been particularly curious about is one of the things you talked about in the last bit of your work, the relationship between giant planets and small planets. Something I was curious if you have any preliminary ideas about is there any indication that the relationship between giants and say super Earths, things like 8 to 15, 20, 8 to 15 Earth masses is similar at all to the relationship between giant planets and inner small rock? Like, is there any indication of the mechanisms by which giants may or may not constrain the two groups of the same?
Yeah, that's a good question. I don't think we have enough giant planets to sort of, or I guess by giant planets, right, you mean the Jovian planets as opposed to the stars,
Yeah.
right? Yeah, I don't think we have quite enough to make that division, but that's a great question.
In CLS is the opposite from we don't have any there, so.
Yeah, maybe we have speakers come up, so we can hear the question.
Can you come up and ask the question up here for the benefit of Zoom?
How many people are on Zoom? Wow, hi everybody. I didn't know you were there.
Right here, is this fine?
Yeah.
Okay. So given that the one system that we know, our solar system, the distribution of distances is so different from most of the other systems, I wonder what kind of selection effects are at play. For instance, is it possible that we are finding systems that have distributions like the kind that you showed? And one way to look at it, and I'm sure you looked at it, is how the average size of multi-planet systems will compare to average sizes of individual planet systems and so on.
Oh, okay, yeah, those are two great questions. All right, so let me address the first one. Obviously, we live a lot further from our sun than most of the planets in the compact multis that I showed you, including the planets in those patterns. It turns out that, all right, so we can do occurrence work, and it looks like these compact multis are ubiquitous, that something like 50% plus of stars have a compact multi-architecture. So we're not great yet with Kepler or other transit missions at finding true solar system analogs with like a rocky Earth at 1 AU and a Jupiter. But I can tell you one thing, which is I looked for planet Vulcan and it ain't there, which is to say, I'm pretty confident that the space inside of Mercury is devoid of super Earths. So flipping the question, right, why doesn't our solar system have these compact multis that are so common elsewhere? And this isn't like the hot Jupiters, where it was like a bunch of them were found because they were easy to find, even though they're intrinsically rare. Just the sheer number of compact multis that have been found indicates that their occurrence is of order 50%, or like of order unity, essentially. So, So I think flipping the question, I would ask sort of how rare is the solar system? And to answer that, we actually have to find solar system analogs. Should I answer your second? I guess I'll briefly answer your second question, which is the planets, the systems that appear to have just one transiting planet likely have other planets that we haven't found yet. I'm still looking for planet 9, right? We haven't even found all the planets in our own solar system. So we're not great at getting the full census of planets in other systems. So if they appear to have one planet, there's a good chance that there's actually more hiding. M stars. All right, the question was M stars. All right, pretty much almost everything I told you about today was for FGK stars, the basis of the California Kepler survey. I did mention that TRAPPIST-1 is kind of useful to think about. It's really interesting. It's a little bit like peas in a pod. It's like 7 Earth-sized planets. They're regularly spaced. They are in resonance, which is unlike the majority of these peas in a pod systems. And it's not clear to me if that's because the star is lower mass or the planet to star mass ratio is higher. It turns out Earth mass planets around a 0.1 solar mass star have a kind of a high mass ratio compared to a lot of the exoplanets that we've found. So I don't totally know what's going on there, but it's really cool. It would be great to get more multis around M dwarfs. Still, most of those are from the Kepler mission. Just the long baseline was so important. That's a good idea for a study.
So Lauren, let me ask you a question, maybe if you want to come down here and get ready. I think I'll probably give a lot time for the last question. So my question, if you could go back to this, one of your don't tweet slides, Lauren,
Oh,
that
good.
shows the outer companions with the 7 orders of magnitude.
Yeah, that's my favorite slide too. Except for Pisonopod. I told you I have too many slides. Yeah.
So you pointed out this really intriguing possibility that a distant stellar companion suppresses the masses of the inner planets. Does it also affect the semi-major axes of the inner planets? It looks like the smallest inner planets that have stellar companions are ultra short period planets, or at least few day period planets.
Yeah, I totally agree, right? These guys are, even the ones that are like kind of more massive, have really short periods. Something that's not well shown here is that a bunch of these stellar mass things are very eccentric. So even though their semi-major axis is like 30 AU or whatever, some of them might have periastron passages of just a few AU. So that might be part of what's going on. I think what I have yet to do is mock up what happens if you swap which are the inner planets and the outer planets in the systems. I think that would be a pretty good test because stability creates bias, right? We only observe the planetary systems that are still around. So I'd really have to see what other combinations of architectures from our sample could be stable to address that question.
Thank you. Last question.
Hi, thank you for a very clear talk. I noticed that as the presentation progressed, I saw fewer and fewer stellar parameters. What would the Pisonopod look like with metallicity, or as an extra axis for metallicity, or stellar magnetic field, asteroseismology? Can that bring the mass into the disk to give the power law change?
So just to refresh you, I know I breezed through all of these patterns. There's only so much we can do in 50 minutes, right? So stellar metallicity is actually here, and you can see there's kind of a correlation here, stronger in a subset that includes diverse planet masses, weaker in the subset that's restricted to planets with very similar sizes, but possibly still there. I don't know if you believe the p-value of 0.01, but I think that actually extending this work to M dwarfs, right, to extend the stellar mass axis, and also extending to low metallicity stars is really important. Actually, a big question in my mind right now is that in the Gaia era, we can identify all these really cool stars that are in the Gaia Enceladus sausage, or brand new open clusters that no one knew about before. We are so much better at kinematically and chemically tagging stars than we've ever been. And I'm really curious how, as you say, how are the planet properties dependent on stellar chemistry and stellar origin in a sense of galactic astronomy?
All right, a reminder, wine and cheese starts now in the back, and let's thank Lauren one more time.